Hi, everyone, and welcome to our webinar, Top TEE Bugs You Should Fix Before Your Audit. My name is Paul, and I'm a security engineer here at Trail of Bits on the cryptography team, and I will also act as your moderator today. So before we get started, let's get some housekeeping items out of the way. Yes, we will record the webinar. And we will also send you the slides. You should get an email with a copy of the slides and a link to the recording about an hour after the end of the event. We also encourage you to ask questions, and we have blocked off some time at the end of the session to address anything that comes up during the session. There is a little icon on the right-hand side of your screen where you can add questions to a chat. So feel free to add questions there, and then we will go over as many questions as we can at the end of the webinar, where we have blocked off some time to answer those questions. I did want to say that while we were preparing this session, we realized that this actually should be a series of webinars. There's a ton of content here, a ton of really good content, and we could really spend hours digging into everything. So there is a chance that we would go over the allotted 45 minutes. Please excuse us if we do, but we'll do our best. But today in this webinar, we will start by looking at an existing TE-based verifiable private AI system. And then we will provide some sort of checklist of all the things that auditors tend to look out for when reviewing such systems. We will just going over the checklist is not very interesting. So we have split up this webinar into kind of like 4 specific spotlight areas. And then we will go over specific items within those higher level areas and do some deep dive into the code as well. I will now switch to this view. And today, joining me, there is Jiden Hess, who is a fellow principal security engineer here at Trail of Bits. And I'm also joined by Jules Green, who is the co-founder of Tinfoil, where he's building verifiable private AI. Before co-founding Tinfoil, Jules was at MIT, where he got his PhD in secure hardware and cryptography. And he also spent some time at NVIDIA and Microsoft Research working on confidential computing. So thank you very much to both of you for being here today. And without further ado, let's dig in. To set the stage, I'd like to ask Jules to provide an overview of the Tinfoil system. Jules, over to you.
Thank you, Paul. And so, yeah, I'm one of the co-founder of Tinfoils, and so we are a startup. Some people also call us a security lab, and so we're a team of PhDs and security engineers from MIT, Cloudflare. As Paul mentioned, we've worked at NVIDIA, Google, Microsoft, Entity. And what we're trying to do at Tinfoil is working in what we believe is one of the most important incoming problem in security and privacy. So I'm sure you've all noticed that AI is getting deeply embedded in all aspects of our lives, and it's quickly becoming maybe the most intimate technological extensions of ourselves. So that counts for our daily lives, but also for professional lives. And so think about how embedded it is in your life today. For a lot of us, for instance, pair programming with AI has become very natural. And so think now about how much more this will be in 6 months, 5 years, or even 10 years. So you can really think about it as maybe has the potential to become an extension of your professional and personal self once again, and like someone constantly standing next to you. And so we think that the only way forward to make that level of exchange possible and not completely awkward is actually to have all these interactions being fully private. And so unfortunately for now, AI doesn't fit in your personal phone or your personal laptop at its full capacity. And that's why we're building Tinfoil, which is verifiably private AI in all of its shapes and forms. So we work with a startup. They're at the frontier of what is possible with personal AI today. We also work with privacy-focused tech companies and larger enterprise in highly regulated industry. And so the way we do all this private AI is by using a lot of TEs, hence the discussion today. So I'm going to start by making things very concrete and presenting a demo over chat here. So you're welcome to also do it at home using the QR code. But I'm going to share my screen here. And so as you can see, this looks like a classic AI chat. And so if I'm asking a question, I will hear, oops, trade-off, but well, we're gonna get something different, I guess. Like we get an interesting answer, and so we support a bunch of different model, including like larger thinking model, where we can ask are the question. Sorry, I meant trail of bits. And the interesting part here is going to be the security of you, obviously. And so here, if you click on our verification center, you're going to be able to see that all the interaction that you're having with the artificial intelligence are actually end-to-end secure and attested end-to-end. And so here you can see that all your data is encrypted using a unique key, but also that all our code is auditable and posted on a transparency log. And then the second part of what we're interested in today is the TE part and the confidential computing part. And here you can see that in the browser, all the attestation, all the kind of cryptographic proof related to the use of TEs are verified right here. And so here you get it right. Trade-off bit is better than trade-off bot. So I will remove my screen here. And so just to give you a quick overview of the system that we're gonna look at today. So when Jaden reached out a few weeks ago and Paul for set up this audit, like we were very excited and obviously had to scope it down. So we decided to really focus on that web chat that I just presented. And so things look more or less like this. So you have the inference server that are running entirely inside of a TE. And so that's on top of computing hardware. So it could be AMD, Intel, NVIDIA. We also have the client, which is what I just showed to you, that runs in the web browser. And so this client is actually going to fetch a bunch of proof and communicate with the secure enclave and verify these proofs using code on build certificate. So we'll go into detail into all of this, but that's the high level architecture. And very quickly, in terms of threat model, historically, when you think about TEs, the goal has been to remove the cloud provider from the trust boundary. But here we're trying to push things a bit further because even tinfoil shouldn't have access to the data exchange by its users, right? And so if TEs were providing like confidential computing, we're trying to build something that's closer to a confidential application forever, for instance. So the cloud provider is not trusted, tinfoil is not trusted, any privileged operator is not trusted. And so you kind of have like this map of different possible attackers that's very large. And so you can think of different attacks that can go from non-invasive and so non-detectable. So that would be like issue with access control, for instance, to things that are a lot more invasive and potentially detectable, like physical attacks. And then there's different types of attacker. You can think of people who are internal to tinfoil. And like, for instance, a rogue tin man, which would be like an employee that has turned evil, or a more outsider threat. And so yeah, here, because we like most of the technology is based on TE, I would say, for instance, physical attacks are not out of scope, but they're best efforts. Like we're limited by the underlying, limited by the underlying primitive, and you definitely more than TE for like a full physical security setup. But there's still like a lot of things that we can do to mitigate the impact of this type of attacks. And for us, yeah, in summary, like the game over is kind of if someone managed to get a hold on both an attestation key from one of these TEs and the tinfoil DNS credential. And so that kind of like create these maps of the different things that are difficult. And so at tinfoil, everything we've always been building in the open since day one. All our code is open source and fully traceable. And so this people looking at it is exactly like what we've been asking for the whole time. And so very excited to discuss what are the kind of bugs that people look at when they do this type of audit. And I'm gonna hand it over to Jaden for going over that list.
Cool. Yeah, thanks, Jules. I want to give a shout out to Jules and everyone at Tinfoil because we kind of jump scared them with this whole project. Basically told them, I don't know, give them a week of heads up that we were interested in publicly sharing all of their dirty laundry and all the kind of nitty gritty bugs. So super cool that they're building in the open like this and willing to help increase security in the space. We have a T sort of bug hunting checklist that is a fraction of all the things that we would do during an audit, but I think gives a concrete way for people who are building these sorts of applications to find the bugs that are most common when we look at T applications. So we're probably not going to have time to go super in depth on all of these points. And if, you can see there's really whole webinars worth of content in things like side channels and physical access mitigations and host hardening, systems transparency. But we're going to kind of do our best on this by going through and highlighting particular segments of code in Tinfoil and showing how they address each of these bullet points, where we found potential problems, where problems often reside, even if Tinfoil had resolved them. And so hopefully this will be useful to you. I'll also point out that in a lot of these issues, they're sort of only issues in a relatively strong threat model, right? So just because I say something like this allows you to extract a TLS key or something, it doesn't mean that you, the audience, could do it. It often requires access to, for example, the credentials for Tinfoil's DNS domain. And I'll hand it over to Jules for talking about how the whole thing works.
Yeah, and so we're gonna separate kind of this list of different attacks or things to look at in different themes. And so the first part of the system that we're gonna look at is the client-side attestation verification. So as I explained, the thread model part, for us, things are a bit different, and we don't trust the cloud, but we also don't trust Tinfoil. So that means there's no trusted third party. And so verification cannot be delegated to an attestation service running in the cloud. And so it's very important for us to run all of this verification client side. So we have a bunch of client SDKs in different language that take care of that. And this week, for instance, in collaboration with the Freedom of Press, we released a JavaScript native client for Sigstore. And that means that we also have a fully web native implementation of this verifier where everything is in TypeScript for speed and convenience. And so that's the very specificity of the Tinfoil system. And I'm going to let Jaden explain how things work very concretely when you verify an attestation.
Yeah. So actually, even before we jump into this, it's worth mentioning that Tinfoil has a JavaScript client, and there's kind of a fundamental issue in JavaScript cryptography where potentially a server can just serve you a malicious client that doesn't actually do any of the attestation verification steps. And I think Jules has some cool plans for how to work around that. So maybe later we can get to those. But setting that aside, let's talk about what actually goes into remote attestation. So the goal is to affirmatively verify that the server that you're talking to runs on genuine confidential computing hardware that protects the data that is being processed from snooping by adversaries who own the server. And there's a few kind of knobs to twiddle in this. So we're going to just jump in and share exactly how Tinfoil does SEV SMP report validation. So this is the AMD version of confidential computing. And so you can see that basically you get some document, and you can assume that this document is signed by a chain of certificates that goes up to a public key root that is owned by AMD. And there's a whole bunch of stuff in this document. So we like to see people binding to a particular model or version of the CPU, because older CPU versions may have public vulnerabilities. The other things are that in AMD, there are these guest policies. These are mitigations that prevent various kinds of attacks. So the most important things are to ensure that debug is disabled. It's relatively common, especially in TDX, to see people fail to validate that debugging is disabled, which allows you to just read data out of the enclave directly. Multi-threading would be best to disable, but requires BIOS flags that may not be available in every hosting environment. This allows multi-threading separate processes on the same logical CPU thread, which allows for higher resolution side channels than you would otherwise get. These all have sort of, are essentially mitigations for known published attacks. There are some interesting attacks where you can essentially make your memory look twice as big as it is and cause memory aliasing, where an unprivileged process can access, say, the high half of memory, but physically this gets mapped back to the low half of memory. And this allows you to circumvent various architectural protections. So the goal here is basically to enable as many of these as possible. Some of them are only available on newer models of hardware. Some are only available on newer BIOS versions. And Jules maybe later can address some of that.
Yeah, I was gonna say that even sometimes, and that's always the challenge, like AMD has announced these flags and they're like in the spec, but they're actually like not reflected or by the hardware, or haven't made it in the BIOS, or sometimes like support in the Linux kernel is also missing, interestingly.
Yeah. So the other important things to note in this report are the actual the measurement here and the report data, and we'll kind of address these later. But the idea here is that by encoding, say, public keys in this report data, you can bind an attestation to a particular trusted enclave and be sure that like the client is only sending data to a public key owned by this enclave. And then the measurement is essentially a measurement of the code that is running in this enclave, because again, if you have arbitrary code, you could just dump all of your secrets to the console. So that's for AMD. There's some interesting things to cover on the TDX side. So one is that this Google Go SEV-SMP verifier library that Tinfoil is using is relatively popular. It has some pitfalls where the defaults are not exactly secure. So, for example, if you fail to specify an expected TD attributes fields in this verification, it will by default allow debug mode enabled enclaves. And also the TCB verification. We're actually going to show this on a new slide. One sec. So if we move up here, the TCB verification basically means that we want to ensure that the enclave is running firmware, like the actual firmware of the device that is up to date. And if the firmware is not up to date, there could be known attacks that allow you to compromise the execution of the system in some way. So the goal is to learn whether or not the system is up to date. It turns out that Intel has a somewhat complex way of determining this, where they sign a bundle called a collateral object that contains a list of all of the current version numbers and whether certain configurations are up to date or have known vulnerabilities. And under the default behavior, the system will accept any basically any TCB collateral that is at least in the most recent 1 year, most recent 12 months. And the problem with that is that this means that if there's a published security vulnerability, you're not rejecting attestations from devices until a year after that vulnerability is published. So we like to specify that there's a configurable level called a TCBR counter, a TCB recovery counter, that is a sort of configurable toggle that's not exposed by this library. And so if you're using this library, I would recommend looking into managing your own TCBR version number. That's the moral of that story. And I think that is all we have to say on TDX quit verification. I don't know, Jules, if you have any background in like how you've tried to wrangle this.
No, that's interesting. Yeah, there's definitely also sometimes a lack of documentation on like these different flags and different things that you can turn on. Like for instance, in the AMD BIOS, like the type of flag that we're discussing, sometimes it boils down to finding the paper that is actually the attack and making like the connection and figure it out like if it makes sense or not. So these are all also things that are interesting to improve in the future and like make more documentation to explain really like what is the implication of each flags and when you decided on your threat model, what you should like enable or not.
Yeah, and I noticed that there's also this other bullet point I can share really quickly. Basically, the AMD SEV report will include these TCP values, basically declaring, I am an enclave and I have version number 6 of each of these different kinds of firmware. Problem is you can't really trust this report itself, because if the firmware is vulnerable, then the system that produced the firmware or produced the report could be lying about what firmware version it is. So what you want to do is match this up with the certificate that's issued from the AMD like attestation service. And so that's where this check comes in that you can see in the Go TDI or Go SEV library, where it actually extracts from the certificate, which says, this is a key that really belongs to this particular enclave, a list of firmware versions, trusted compute-based versions, that it then matches against the ones reported in the report itself. So this is an easy to miss check if you're rolling your own attestation library.
Great, thank you both. I think that really nicely sums up this first topic. Kind of sounds like the main things to look out for are those flags that need to be enabled, and maybe Joe was highlighting some documentation issue as well, where it's not always clear what needs to be done when using those underlying libraries. So I'll hand it over back to Jules, who's going to talk about our second spotlight here.
Thank you, Paul. So yes, spotlight 2, attestation transport. So here the question is, how do you make sure that all your data is encrypted and sent over the network with a key that's only accessible to an enclave, right? So how do you establish that? And most of the time, I mean, what you need to do is to bind this transport to an attestation proof, right? So here we're going to talk a bit about the specificity of the system that we're looking at. We're using a web chat that runs in the browser, right? So usually what you would do is use a TLS connection and verify that the certificate of the TLS connection is endorsed by the attestation report. But the problem in a browser environment is that you actually cannot get access to that certificate to check that it indeed corresponds to the TLS connection that you're currently having with a given domain. So this is like a bit of more of a zoom in of the architecture of exactly how the request travels when you use the chat. So you're going to have a TLS connection to a first enclave that is what we call our model router, and then this model router is going to talk to the inference server specifically. So between the inference server and the model router, we can use attested TLS normally, but between the chat and the model, because we cannot get access to that certificate to verify that it's embedded in the attestation, you only have access to, if you only use TLS, to what we would call audit time security, which means that you will need to audit all certificates emitted for that domain retrospectively and make sure that they were all embedded in an attestation report. And so here what we do is that on top of TLS, we also encrypt the body of the request using HPKE, which is a standard for transport encryption. And that makes it possible to have the public key of the HPKE exposed to a JavaScript verifier to verify the binding with the attestation. So I'll hand it over to Jaden to talk about the specificity of how you think about transport attestation in general.
Yeah. So the goal, right, of attestation is to ensure that only an enclave which is able to produce a valid attestation is able to participate in a session with the client, right? So the client's data is only ever sent to such an enclave. Responses to the client are guaranteed to have come from that enclave. And beyond that, because there are so many potential attacks against TEs from the physical standpoint and from like side channels, it is really best if your attestation is fresh. So if ideally each attestation is produced in a way that is bound to a particular session with a client, which guarantees the client that the other end of the particular channel which they are using to communicate belongs to a trusted TE. The way that Tinfoil does attestation currently is that, let's see, they remember we looked at that document earlier, which basically, let's see if I can basically prove that there was in the world somewhere an enclave with the proper measurements. This is where we extract from that report data a pair of keys, in this case, that are the public keys for the particular enclave the user is talking to. So this actually is not strictly bound to a particular session. This is only a binding between an enclave and a particular public key. And so this could lead to some concerns with, say, a key extraction attack allowing an attacker to impersonate a TE even when they no longer have access to the particular TE that they're impersonating. Yeah. So the interesting things here are, why is there an HPK key and a TLS public key? Well, Jules already talked about it. It's hard to use TLS from within a browser context, so they use this HPK protocol. We actually found some interesting things in this HPK protocol. We'll probably not be able to easily see here how this works, but maybe just knowing what headers are in there are pretty interesting. So in the current version of the spec, the request headers are basically the user sends what's called like an ephemeral key or a key encapsulated key. And this is like a one-time secret used to establish a channel with the enclave. Then the server in the current protocol basically derives a symmetric secret key using this client randomness and decrypts the encrypted HTTP request, generates some response, re-encrypts that response using the same key, and then ships it back. And this binds the response to the request and makes sure that the response can only be read by the client. It notably doesn't do anything like complex sequencing of messages. This is a one-shot kind of there and back protocol. If the server was stateful, we would want to see something with a little bit more sort of session binding where you can prevent reordering attacks and replay attacks. The version we looked at before this most recent change actually sent along with this initial message a client HPKE public key, and the server would re-encrypt the response to this client HPKE public key. But because that HPKE public key was not actually authenticated, it could be replaced by a man in the middle, allowing a man in the middle to basically receive all the responses coming out of the TE. So, the moral of the story here is be pretty careful when building out the transport encryption. Try to rely on things as close to standard as possible. If not, consider modeling your system in something like ProVerif. And there's also various other properties that you might want out of a system. There's been decades of research into transport encryption and authenticated key exchange. So, try to use as much of that body of knowledge as possible. For example, in this scheme, there's no forward secrecy, right? So if the HPK key of a TE is ever extracted after the fact, there would be the potential for an attacker to decrypt all the messages that had been seen over the channel. This is a pretty obscure threat model. It requires you to assume something like you can extract a key from a live CVM after the fact, but it's not impossible. So we can hand that to Jules.
Yeah, very cool. No, that there was a lot of great content. It's always yeah, as you're saying, like most of the attack require a rogue tin man, so someone from like inside the organization to actually mount side channels or mount like physical attacks. But yeah, they're definitely like interesting to address. And I think ideally what you want is to have like fresh attestation on every exchange or like every key, and like rotate your key very frequently. So even if you have a key extraction or something like that that is possible, you have these kind of things covered.
Yeah, maybe to throw in one last comment. How do you do this in maybe the optimal way? There's actually an IETF working group that is putting together a spec on how to do attested TLS. The general takeaway should probably be that one of the better ways to do attested transport security is to use TLS 1.3 and then use an exported authenticator, which is basically some key material you get out of your session that allows you to bind to a particular TLS session. This, of course, is like difficult in the browser. So if you are working in the browser, you may need to make some compromises.
Yeah. Yeah, and for instance, that's what we do for enclave to enclave communication, or like with any other of our SDKs or not in the browser. Okay, should we move to the next spotlight?
Yes.
Okay, and so spotlight number 3 is confidential VM. So we saw the client and how it communicates with the enclave. So now we're going to talk about what is actually running inside of the TE. And so the goal here is that we wanted something that was fully open source, obviously, for auditability and traceability and code transparency. And we wanted something that support all types of hardware, so Intel, TDX, NVIDIA, and still be minimal and hardened. And so that's kind of the way you approach that piece of the system. And so I'll hand it over to you, Jane.
Yeah. So there's potentially quite a lot of content here. So we're going to try to just get the highlights. The general goal, right, is that you have some CVM that's running, a confidential virtual machine that's running, and you know that it's a genuine enclave, but somehow you need to know like what code is running in that enclave so that you know it's not just like some random guy's like Ubuntu box that you can SSH into. It's not just dumping all of your measurement or your chats to the console. And so the question is like, how does all of the code running on the machine end up in this little, one single hash that is included in the report? And the basics are that, let's see if I can get some code going here. Basically, the idea is that you can measure all of the code that runs at boot to give you a static root of trust. And then if you include in that code that runs at boot hashes of your kernel, your initRD, and your kernel command line, then you know all of the code that is booting sort of as your operating system comes up, right? Then because the kernel command line is included in that initial measurement, you can shove things in it like hashes of your root file system and any sort of static configuration data like so. And so on AMD, this is all kind of ad hoc for the most part if you use the default build stack. There's nice projects like Stage Zero, which try to make this like a little bit more abstracted and comprehensive. There's also things like Coconut SPSM, which try to kind of give runtime PCR-like functionality. Intel is actually somewhat easier. Intel uses these things called RTMRs, which basically are like runtime PCR-like registers that allow you to do things like shove your kernel command line into a particular register at runtime rather than having to encode hashes of all of these things at boot time. The other important things to note, things that we see go wrong, are this. We briefly showed where the root file system hash lives in that kernel command line. There's a question of how do you actually check that the disk, you're given some large disk that contains the root file system that may not be able to fit like entirely in memory. And you want to be sure that the disk that is given to the virtual machine matches this hash, which is like a known good hash that comes from some build system. And so what we can do is use this great little tool called DM Verity, which essentially acts as like a runtime integrity tree where every access to the block device actually goes through basically a Merkle tree verification to ensure that it is like the correct piece of data for that location as indicated by the like cryptographic commitment root digest. And so Tinfoil uses a kind of automated form of this called systemd Verity generator, I guess. And so you can specify your partitions, and then you can encode basically the idea that you want this root partition to have an associated Verity partition, which encodes like metadata for Verity, all the intermediate hashes, and then this Verity match key kind of matches up the like auxiliary disk with the main disk. So they do that pretty well. The pitfall we see here sometimes is people try to use something like Lux, where they, instead of using a read-only Verity disk, they use a encrypted disk that provides sometimes some sort of integrity protection. In almost all cases, this integrity protection is not sufficient for like code disks. And so you really should be using something like DM Verity rather than any sort of encryption. Another interesting pitfall during the boot process is that your initRD, if you use a default systemd initRD, often has emergency consoles where if a device fails to mount or there's some other error, you can drop into an emergency console that kind of bypasses all of the normal login systems and just gives you like immediate access to your CVM. And because this happens after like the initial code measurement is put into the measurement register, anyone who's able to get access to the CVM at this stage is able to generate attestations basically over anything they would like, and thus impersonate a genuine CVM and steal user data. So you can see here that in the initial version we reviewed, there was commands to prevent these serial and console services that you would normally use to log into the system. These are actually not sufficient, and so you need something that includes these emergency shells. And in fact, you need to ensure that these shells are not present in initRD or in like the runtime systemd. So Jules very quickly patched that up, and I think that's one that people often are not even thinking about when they're building these systems.
Yeah, it was interesting to realize that I thought like basically disabling all console access would be enough, because if you can't get like access to a shell, like even if the shell pops up, like there's no way to get to it. But yeah, it was really interesting to actually realize that the default behavior on a vanilla Linux kernel is actually to include a VGA console that is selected by default if not specified in the command line. And so, yeah, the actual reasoning of like, oh, as long as I don't have a console in my command line that would be attested anyway, I'm actually good to go, is not valid if you don't have a hardened kernel. So like, yeah, I guess defense in depth would be removing all the default console from the kernel, but also like enable all this masking and all this blocking at the earlier stage to make sure that there's really like no way to actually get access to a prompt.
Yeah, I'd also point out like another thing that people don't often think about with the kind of CVM hardening scenario that is a little bit scary is that in the malicious hypervisor threat model, you can imagine basically that the hypervisor can delay the execution of pretty much any process by causing like repeated page faults, for example. And so if you have any race conditions on your system, like an adversary can potentially win every race every time. So that's just like one other thing to think about, where this sort of like early boot kind of issue could come up, right? If you have anything that is running that's goal is to check whether something else is running properly and kill the system. If not, you have to make sure everything is like strongly serialized so that you can't bypass protections by just winning race conditions that are not usually observable. So yeah, the other component of the CVM measurement itself is you need some way of attesting devices like GPUs, which are going to receive confidential data, right? So when you're doing inference, you have to actually send the prompts tokenized to the GPU. So the way Tinfoil and most others do this is they're using the NVIDIA NVTrust tools. So there's like two potential modes, one for multi-GPU configurations called protected PCIe. This actually doesn't encrypt the GPU to GPU communication, but frankly, in most threat models where you're worried about someone sniffing on your NVLink, like you're already kind of screwed. Then in the single device attestation, they use just the regular confidential computing system. I generally would prefer seeing custom use of the SDK underlying this NVTrust library rather than the out-of-the-box attestation. There's like a lot of knobs to turn, and while these are probably sufficient for most use cases, it's worth kind of knowing what's in there. Another interesting question for this sort of device attestation are things like certificate revocation and kind of freshness in general. How do you get the most recent firmware versions? How do you check whether the certificates for a particular device are revoked? These are both tied into questions of like, how does the CVM itself acquire a trusted notion of external time so that it can do things like certificate revocation checking? So there's sort of a laundry list of things that can be followed on to just the basic, is this attested in like a longer audit? So then, yeah, Jules already talked about CVM to CVM attested TLS, right? So in this system, they use TLS between the CVMs, even though they use HPKE sometimes to the client. And, that is nice. You always have to make sure that the CVM that's acting as the client is able to verify things like SIGSTOR, binary transparency logs over the measurements that are produced by the backend CVM. And this also ties into things like trusted time, revocation checking. How do you know that your router CVM is talking to a system that is like a current up-to-date system? Okay, and then last, so a big source of errors, and it's hard to give kind of a single point of failure here, is configuration injection. So in general, you're going to need some way to insert kind of runtime non-attested configurations into the TE. And often this is a source of code execution vulnerabilities. So for example, the way that Tinfoil is doing this, they, sorry, one sec. They have this external configuration file, and this includes some things like Google Cloud credentials to pull Docker containers. And so this is not included in the attestation. So any way that someone tampering with this external config file could get something like code execution would be a serious problem. There's no real exploitable issues here currently, but you can see that there's sort of areas where I'd be a little concerned. Like, this command here, is pulling some data out of this external configuration file, and then it's passing it as arguments to this gcloud auth command. This is like a pattern that we sometimes see leading to command injection or argument injection vulnerabilities. So for certain types of commands, if you're able to pass arbitrary arguments, you can kind of leverage those commands into doing more work for you. So, you can imagine if this was piped to like find or something, that you could use the argument splitting of this command to get like arbitrary code running on the target. So, I honestly, I couldn't tell you exactly what all the different commands to gcloud auth are, but in theory, one could put essentially any series of commands using this external arguments to gcloud auth using this external config file. And yeah, that is that for how to secure your CVM. Jules, you were
Jules.
Sorry, I muted myself to drink water. So yeah, we're gonna talk about the last chapter of the talk, which is binary transparency. So tinfoil is completely open source, and every code that we publish on GitHub is automatically compiled, measured, and these reference measurements are published on a transparency log. And that makes it possible for our client-side verifier to independently get these reference measurements to verify them against what is provided by the TE, right? And so I'll hand it over to Jaden on specificity of how to ensure you have the correct measurements on the other side.
Yeah, so this is an interesting topic, right? Because there's sort of a long chain of provenance that you want to maintain. Ultimately, your goal is that the CVM image measurement is strongly connected to some publicly visible build flow in a repository somewhere. And so the question is, how is that actually connected? So the way that Tinfoil does it is that they have a build action in their GitHub repos that runs on push, and it uses this tinfoil sh private build action repository, and that in turn runs a series of code that basically fetches the build artifacts, compiles them into a sort of a bundle, and then measures the results of sort of executing this code in AMD and in Intel. And so we found a couple interesting issues in the way that this is handled exactly. So for one, when doing this measurement for preparation to post the measurement to the transparency log, the build process actually fetches the kernel and initRD file from this images.tinfoil.sh server. So when the image is built, it gets uploaded to the server, and then when the attestation step happens, it gets downloaded from the server. And in the middle of there, tinfoil devs could have swapped the image out for a malicious image, for example. So it's important to check these images that you're fetching against some like known good hash that you fetch from the build process of the previous step. So this has been changed in the latest version to fetch the hashes of the kernel and initRD files from a sigstore attested manifest, and then check them against the downloaded images, right? So you have this step where you have the built CVM. You want to turn that into AMD digests and Intel digests, and there needs to be some like chain of provenance between the two there. There's sort of similar issues in the actual workflow for that action that does the computation of the measurements. So when that action is running, it actually was pulling this GitHub container repo, right? That this sort of Docker image from a GitHub container repository. And the issue with this is that like anyone with write access to the tinfoil sh org is actually able to overwrite versioned images in this repo. So it's possible that someone could replace the Docker container that does the public, the trusted attestation publishing with something that does a malicious publish of a malicious digest. So this also kind of needed to be pinned to a specific hash of that Docker image, which also then in turn needs to be sourced from a sort of transparently verifiable like build system. So this all kind of goes to show that especially in a multi-step chain build process, there's kind of a lot of potential ways that you can drop the ball and allow someone to slide in untrusted code or data into the build process without really realizing it. Right? This is just a totally different way of thinking about CI/CD than your typical open source repository.
Yeah, I will mention that I think also the way we're thinking about it is like really providing like transparency of the binary at audit time, right? So like these are meaning that even if like something would be compromised eventually, like the measurements are like published on the transparency log are pinned to binaries that are auditable and that you can download and observe. And so this hardening of the build chain is absolutely like very necessary, but you still have like the possibility to audit the pieces or like pin on the transparency log at the end, regardless. Yeah.
And then, okay, so we're not even going to really talk about these. There is a whole nother potential hour-long webinar to be had on side channel attacks, physical access-based attacks, how to do more host side hardening and transparency, how to do more guest side hardening transparency. I think it's worth calling out that in these LLM-based systems, the things we're most concerned about are things probably like memory access pattern-based side channels that allow you to, for example, snoop on what the tokenizer is doing, which could potentially directly leak user kind of prompts. In general, there's a lot of effort put into side channel resistance in cryptographic libraries, but your typical application is not designed to be resistant to side channels from a malicious hypervisor. So you still have this application data to protect. Most of these threat models, of course, require kind of logical access to the host, which requires in their threat model like a tin man, or at least someone who has access to the DNS credentials for the tinfoil.sh domain. But there's just many months worth of content that could go into making a system end-to-end secure.
Yeah, and I guess here's something interesting that you mentioned, that we try to make sure that these attacks are only possible from an internal person that would have like very high privilege access to be able to even try mounting them. And I think that the key here is to like all attestation or all like material that's like signed by a TV is also like double signed by tinfoil in some ways, to make sure that it comes from like inside the company, it comes from one of the machine that we've like vouched for, and that it's not from a TE that comes from like someone else that could have potentially like extracted the keys, that has nothing to do with tinfoil and would still be able to compromise tinfoil. So that's like the kind of basic things that you can do to still like mitigate the risk of this attack and make sure that an attacker would have to also like penetrate the organization first. Yeah.
Awesome. Thank you both so much for the really good and in-depth content. We're running a little late, but actually not too late. So we have some time for a Q&A. And I see there's been a lot of chat in the public chat here. So I'm going to pick a couple of questions that Jaden and Jules can try and answer. So the first one here will be, which attested TLS protocol do you use? And I believe there may be a kind of a related question to that. I see another note further down, which is that putting just the public key in report data is insufficient. So maybe you wanna speak to that, Jules?
Interesting. So, I mean, as we explained, like, especially in the web browser, like TLS is probably not sufficient because you can't actually like check that the public key that is using for the connection is connected to the attestation report. And so we have this extra protocol that actually like encrypt the body to make sure that that is actually connected to the attestation.
Yeah. So I mean, I can maybe jump in and comment a little bit. So there is an attested TLS step in tinfoil currently between the CVMs. It is using just attestation over the public key. The concern that could be raised for just attestation over the public key is that in the case where the public key is potentially extractable from a CVM, or where you can produce an attestation over a public key which never resided in a genuine CVM, then the user has no assurance that the endpoint they're talking to is a genuine CVM. But again, like this requires pre-assumption that someone has at some point extracted a key from the CVM. So it is better, when possible, to bind to a specific TLS session by like putting the exported authenticator from a TLS session into the attestation report. But currently, tinfoil is just using kind of the plain attestation over the public key version. There's other potential ways to do browser-based kind of encryption. We talked about with tools like potential to do noise or something like that. Problem is that on the JavaScript side, the set of like good transport encryption libraries is not great. So this is an engineering effort.
Yeah. And I mean, HPK is like well implemented. Like this is also like one of the building blocks of OHTTP, for instance. So it's like there's a lot of good implementation out there, reference implementation, like in JavaScript, in Rust, and all that make it possible to like stick close to a standard. Yeah.
Good. Next question. Do your attestations include measurements of your application code or just of the firmware, kernel, platform config, etc.? I know that SCVSMP and TDX attestations only attest to the platform by default, but if you want measurements of your application, you need to deploy some sort of VTPM in the trusted VM to measure the application.
Yeah, so I can answer this one. Yeah, that's that. I had a very good graph that was a bit complicated that I removed from the slides for that. But basically, the way we do it, so VTPM has like a bunch of drawbacks as you're highlighting. Like for instance, you now have a key that lives on the CPU that's like sensitive to side channels or things like that. So what we like to do is to bind as many things as possible to actually like the hardware measurements. And so the way we do it currently is to put things inside of the command line. So you're gonna have the tinfoil config that contains the application basically measurements that is gonna be hashed and put inside of the, so this is the root hash, so that's for the disk. But if you keep going further, yeah, exactly. Tinfoil config hash, like this is actually gonna be our application level measurements, so at least the beginning of the binding to that. And so all of that goes like directly inside of the command line and is signed by the AMD coprocessor or the Intel like the Intel attestation mechanism. And so that makes sure that all attestation signatures are like not dedicated to a VTPM or something like that. But VTPM is a great option, I think, when you want to have maybe like more homogeneity across platforms maybe, and like it's at the same time like very complex to use, potentially a little bit more standardized. But yeah, I'm curious your opinion on that, Jaden.
Yeah, and I'd also point out that actually TDX does provide something pretty similar to a TPM style API where you can read like application level information into the RTMRs that are kind of like extend only hash based registers. AMD does not provide anything like this by default. You can build in sort of a separate underlying layer running at a different privilege level that kind of acts like a VTPM basically. But that requires, like Jules said, kind of extra long-lived keys that are present on the CPU. The other thing to note is that this command line is included in the initial memory. Well, a hash of it is included in the initial memory image, and that transitively ends up in the AMD report.
Yeah, and the command line makes it possible to have something like consistent between Intel and AMD. Yeah, and also an issue with VTPM in some implementation, like for instance, like on public cloud is that the parallelizer might be actually closed source, and so that actually like you're bringing in a lot of new assumptions on that code that now lives inside of the TE. So if the goal was to remove trust in the cloud provider, you're back with the with a bunch of code inside.
Great, thanks you too. We'll take one final question by another attendee, which is there a way to attest the BIOS versions and configuration against known secure configurations?
It is difficult. I mean, if you have a TPM built into your system, you can do TPM attestation to get like boot time sort of issues. There's also this cool project called System Transparency that is trying to do kind of fully open source, basically from boot through measured boot through like TPM, etc. So go check them out. In general, this restricts your ability to host the system on different hosting platforms and physical hardware, right? So you're going to end up binding yourself very tightly to a particular machine and particular like set of hosting providers, and that can be challenging operationally. But there is, I think, significant value in being able to verifiably show that no one is running malicious code at the host level either, because that's just like a very high leverage position.
Yeah, and I think like talking about like side channel in general and these kind of things, I think it's also interesting for type of AI workload that we're talking about, that the initial concern for this kind of attacks are in a multi-tenant cloud where you have like a bunch of different users that can run their arbitrary workload in different VMs. And here we're on very different, like there's kind of a change of type of workload. With AI, you need like all the GPUs you can and all the thing you can. So most of the time, like these machines are kind of running a single task, a single program. And so that's a very good fit for trying to do like attestation that go broader than just the T, that actually like would include like the entire stack. That's basically the design, for instance, of a Apple private cloud that attests everything that's like present on the machine. And that makes it very convenient to prove that you don't have an attacker's a piece of software that could act as an attacker that's present anywhere. Because by definition, for all these microarchitecture side channel, you need the attacker and the victim to share like the channel that's going to be exploited.
Thank you, Jules. And with that, we're going to conclude. I want to thank the audience for attending and asking really good questions. Feel free to reach out if any of your questions haven't been answered. Our contact information is there on the page. And again, you'll receive a copy of the slides. And I want to thank Jules and Jaden for the deep dive today, which was super informative, and hope it was informative to the audience as well.
Thank you so much. Thank you, everyone.